Okay, this is practice 6C. We're looking at the answer key, and here's how we do it. So we know that for a molecule of methane, each carbon has 4 electrons. There are 4 hydrogens, and they each have 1. Remember, we're getting this from our periodic table, and that means we have a grand total of 8 electrons. We'll put our carbon in the middle. We'll draw our skeleton structure so that every hydrogen is evenly spaced, nice and simple. And remember that each of these lines represents 2 electrons. That means we've used up 8 electrons in the bonding. There aren't any left, but what's cool about this is we know the carbon has access to 8, 2, 4, 6, and 8. And what does it say over here about hydrogens? Hydrogens can only hold 2, and that means that you're not really looking at an octet for hydrogen. You're kind of looking at a duet, which means all they can hold is 2. And that means all of these hydrogens are perfectly filled as far as they can go. That means that Lewis structure works for methane. Let's keep that in mind as we're doing number 2. Water. We know there are 2 hydrogens. They each have 1 electron. There was 1 oxygen, and that has 6. That means we have a total of 8. Let's put our oxygen in the middle because we're trying to keep everything as simple as possible. And that means we've used up 2 and 4 electrons in the bond. Now we have 4 left. Well, after we've done all the bonding, what's the last step? That one is this one. Any remaining electrons that we have left over after we've filled the valences of the outermost ones go around the central atom. What we have here is a situation where hydrogens can't hold anymore. There's no more room, and yet we still have 4 extra electrons. So we're going to put those around the center atom. I always draw this shape around them. And so that means that these hydrogens have access to 2, which is all they can hold, and the oxygens have access to 8. And so this structure here is the Lewis structure for oxygen. And we'll leave it just like that. Okay, let's do nitrogen triiodide. This one is a molecule that looks like this: nitrogen and 3 iodines. Each nitrogen has got 5 electrons. We have 3 iodines, and they each have 7. That means we have 21 plus 5 is 26. We'll put our nitrogen in the middle. We'll put 3 iodines, 1 on each side, just because it's simplest, and that means we've used up 2, 4, 6 electrons on the bonding. That means we have 20 electrons left. Where are we going to put them? I'll fill the valences of all the outermost atoms first so that they have access to 8. I had 20 electrons to play with, and I've used up 18. That means I have 2 left. Where am I going to put them? Around our central atom. Well, that one works. Everyone's got 8. Well, let's do these bottom 2 first because they're way simpler than they look. Here's the sulfide ion with a charge of 2 minus, and that means that normally it would have 6 electrons, but it has an extra 2 because of this charge. Well, there's only 1 atom, so where am I going to put these? 1, 2, 3, 4, 5, 6, 7, 8. That's that one. How about the hydride ion? It has 1 electron because it's hydrogen, but it has an extra electron because it is an ion. That means it's got a total of 2. Well, hydrogen can only hold 2. So there's that one. All right, let's take a look at these 2 up here. Here is the nitrite ion, and it looks like this, NO2. And it has a charge of -1, which means it has an extra electron. The nitrogen has got 5. There are 2 oxygens, and they each have 6. Plus 1. So we have 12 plus 5 is 17, plus 1 is 18. put the nitrogen in the middle just because it's simplest. And I've used up 4 electrons here and here in the bonding. What that means is that I have 14 electrons left. Well, I'm going to fill up the valences of the outermost ones first, so I'll put 6 around this oxygen so that it has 8. I'll put 6 around this oxygen so that it has 8. And of these 14, I've used up 12, and that means I have 2 left over. We always put the 2 around the central atom, but if you look closely, you'll see that this nitrogen is getting the shaft because it only has access to 6. 2, 4, and 6. So what I'm going to do is I'm going to use a pair of electrons from this oxygen here, create what's called a double bond here. And now what we have looks like this. So the Lewis structure, because we don't typically draw the dots around the outermost atoms, is going to look like this. We have a double bond on this oxygen, and a single bond on this oxygen, and 2 electrons are on the nitrogen. And if you wrote it going the other way, it would be just as valid. Okay, last one on this side. The chloride ion with a charge of -1. We have 1 chlorine and 3 oxygens and 1 extra electron. So this chlorine has got 7. There are 3 oxygens, each with 6, plus 1 additional electron. That means we have 18 plus 7 is 25 plus 1 is 26. So we're going to put chlorine in the middle. We have 3 oxygens, just keeping it simple. And we've used up 6 electrons in the bonding, which leaves us with 20. So I'll fill the valence of this oxygen with 6. Of our 20, we now have 14 left. Fill the valence of this oxygen with 6. Of our 20, we have 8 left. I'll fill the valence of this oxygen with 6. We have 2 left. And we'll put those around our central atom. So the Lewis structure of this one, if we eliminate all the valence electrons around oxygens, we don't need them. It looks like this. Okay, let's go to the back side. This one's going to be tricky. We're going to need to use that double bonding trick that we saw using in the nitride ion. We're going to use that here. So, methane looks like this. Hang on just a second. Sorry, we had a glitch. C2H4. That means 2 carbons, each with 4 electrons, 4 hydrogens, each with 1. That means 8 from the carbon and 4 from the hydrogens is 12 electrons. I'm going to put the carbons in the middle. It doesn't make sense to put the hydrogens in the middle because we can only bond one thing to hydrogens because they can only hold 2. And so what I've done is I've used 2, 4, 6, 8, 10 electrons in the bonding, and that leaves me with 2. So where will I put them? I'm going to draw these hydrogens a little differently so this makes a little bit more sense when I do it. I'm going to take these 2 extra electrons and I'm going to put them around this carbon. And as you can see, this one has access to 8. 2, 4, 6, 8. But this other setup here is a little janky because we are still short a couple. So how are we going to do this? We'll take this extra pair of electrons that isn't doing anything, and we'll actually put it in the middle so that now this carbon has got access to 8, and this carbon has access to 8, and the hydrogens, which can only hold 4. So the Lewis structure is going to look like this. Okay, let's keep going. We're almost done. Hydrogen peroxide. Pretty easy. H2O2. 2 hydrogens, each with 1 electron. 2 oxygens, each with 6. And so what we have looks like this. 2 electrons from the hydrogens, 12 electrons from the oxygens gives us 14. Doesn't make any sense to put the hydrogens in the middle. So just like in the previous example, I'll put the oxygens in the middle. We've used up 2, 4, 6 electrons in the bonding. That leaves us with 8. Well, I can't put these 8 electrons around any of the hydrogens, so I'll put 4 of them around this oxygen, so it has 8, and 4 of them around this oxygen, so it has 8. All right, we're almost done. 2 more. This one is called nitrogen. It has 2 nitrogen atoms, and that means that there are 2 atoms each with 5 electrons, for a total of 10. Well, there's nothing around the outside, so we'll just stick one next to the other, and that means that we've used 2 electrons in the bonding, and that leaves us with 8. So those 8 remaining electrons, I'll put 2 around this nitrogen, and another 4. And the remaining 4 electrons, I'll put 2 around this nitrogen, and another 4. I don't have any more electrons left, but I'm stuck because neither one of these nitrogens has enough electrons. So I'm going to use this pair and this pair to create what's called a triple bond. And now if you're counting, this nitrogen has access to 8, and this nitrogen has access to 8. So to keep it simple, we'll just draw it like this. All right, last one. This one is called boron trifluoride, but look at this asterisk. It means it's called an exception to the octet rule, and there are some that just do. Here, it says here, boron has got 3 valence electrons, and because boron tends to form bonds in which it is surrounded by only 6. In boron trifluoride, for example, the boron atom is surrounded by its own 3 valence electrons, plus 1 from each of the fluorine atoms bonded to it. So, right there, that means it has 1 boron and 3 fluorines. Let's draw it. Boron has got 3 valence electrons. There are 3 fluorines and they each have 7. That means we have a grand total of 24. We'll put the boron in the middle. It only has 3 fluorines, so the simplest design looks like this. We've used up 6 electrons in the bonding, and that tells us that we have 18 left. Of those 18, I'll fill the valence of this fluorine so that it has 8. I'll fill the valence of this fluorine so that it has 8. I'll fill the valence of this fluorine so that it has 8. We've used up 18 electrons, and there aren't any left. And so how are we going to do this? The cool part is that this asterisk tells us that we don't have to do anything else because boron, as this particle says, is surrounded by its own 3 valence electrons and 3 fluorine atoms. It violates the octet rule, and every time we see this little asterisk, it means that we can just leave it alone. So the answer to this one looks like this. Boron with 3 fluorines, and that's all we do. All right, see you on the next one.